exam, you are experimenting. Because experiment is actually going to lead to an outcome. Outcome that may be favorable, an outcome that may be unfavorable. So why is it that outcome can take that to nature? Because we live in a probabilistic environment where there's variations. You could have different kind of outcome depending on how you prepare. So experiment is an act of performance. A trial that generates an outcome. That's what we mean by experiment. So in a stochastic environment, in a probabilistic space, we perform experiment. Your life itself is an experiment. Now, when you perform experiments, there are possibilities. Okay? Even before you go into experiment, we know possibility. You know why? If you are a politician, before you go into election, you know possibility. You know that it's either you win or you lose. Even before going into, before competing, before writing the exam, you know possibility. So what do we mean by possibility here? We're going to call that sample space. Okay? Possibility. So it's what we call sample space. The possible result of an experiment. So when you perform an experiment, the possible outcome that you could have is what we call sample space. If you want to understand statistical theory, you need to be able to understand possibility. Okay, now I want to do this. You know what experiment means, but when you are performing experiments in a stochastic environment, we normally have more than one possible outcome. An environment where there's only one outcome, okay, that very environment doesn't exist. You know what I mean? Environment with only one outcome is the same, is synonymous with, situation where we're going to be happy all the time. I wish we should be happy all the time. But our environment doesn't exist. The environment that exists is a multi-state environment. Multi-state. Okay? Multi-state environments. Okay? Okay, we have one state, but this only occurs in theory. One state is where there's no variation. But multi-state, we got variations. And in a multi-state, more than one possible outcome. And that is what makes us worries. Otherwise, we're never going to be worried in life. If it is going to be just every day I'm going to be happy, today I'm happy, tomorrow happy. I will never be worried about tomorrow because I know it's going to be happiness. But that doesn't happen. It's a mixture, and that's why we get worried. Okay? So that's what we mean. Now, if you take a look at what I said here, I said an experiment is said to be random if it has more than one possible outcome because we live in a world where we're going to have more than one possible outcome, then it's going to be random. Then we're going to be talking about random experiments. Okay, if we talk about random experiment, then it means that is different from a deterministic one. A deterministic one occurs only in one state. The random one occurs in a multi-state. Does that make sense? Now you understand what random experiment. The random experiment is just talking about you trying to repeat. Maybe you repeat your trial many times and you are getting different results. Even you are using the same, just like you are in a company, you are using the same equipment. You use the equipment all the time, you get different results. The same equipment. Then that's a random experiment performing. Okay. Now, I want you to understand the genesis, the background of this. If you understand the background, if you understand the connection, you're actually going to be fine with statistical theory. Now, I just explained something here. Let me tell you this. Because we're performing random experiment that generate different outcome, then we need a model to do that. We need a model because there's randomness. When there is randomness, there will be uncertainty. If there is randomness, there's also going to be uncertainty. Okay? If there's randomness, because we just acknowledge the fact that the experiment we are performing is going to be random because it's generating different outcome. Okay, now there's going to be randomness, there's going to be uncertainty. If I want to use a model to characterize situation, I need to use a model that reflects, that can capture randomness and capture uncertainty. And what kind of model is that? Probability model. Probability model. Okay, probability model is a mathematical framework. Okay, the mathematical framework that will enable you to describe the randomness and uncertainty. And when you are able to describe randomness and uncertainty in a system, that will enable us to take a decision that we are never going to regret. We don't want to take a decision that we will regret. And that is why we need to be able to use a model that commiserates with reality. Reality is probabilistic. So if I want to understand reality, then I'm going to use a probability model. Does that make sense to everyone? Now, let's come to probability model now. What do we mean by probability model? Okay, how do we normally have it? The probability model is going to come in terms of a triplet. This is a triplet. Please pay attention. Probability model is going to come in terms of a triplet. You don't forget the probability model is the one that I actually would use, is the one that will provide a framework, a mathematical framework that will enable us to describe, the uncertainty in the system, the randomness in the system. Now, what I'm trying to talk about now, how does the probability model look like? It's a triplet. And let's discuss the triplets. The first in the triplet that we call the omega is the sample space. The sample space is the one that gives us the possible outcome in the experiment. The second in the triplet is what we call sigma algebra, calling F. Sigma algebra. Okay, we call that sigma algebra. Okay, or sigma algebra. Okay, the sigma algebra calling F, the sigma algebra calling F is what we call collection of events. Collection of events. Let's talk about collection of events. Because you know why? When you perform experiment, there's going to be different kind of events. Okay, the collection of events is what we call the sigma algebra, is what we call the calling F. Okay, that is what we call the calling F. Then the third is a probability measure, a function that assigns probability to every outcome, because in a stochastic environment, whenever there's an outcome, there's a probability associated with whatever outcome. If you pass, there's a probability associated with that. If somebody fails, there's a probability associated with that. Any outcome in a stochastic environment, there's going to be a probability assigned. And what assigns probability to every outcome is what we call probability measure. Do you understand the story now? So probability model will come in terms, in form of a triplet. Okay? The first one, omega, that we call sample space, that contain the possible outcome. The second one that we call sigma algebra, that we also call Collinet, is a collection of events. And the third one is a probability measure, a function that assign, that assign probability values to every outcome. Now, you know what I want to do now? I want us to go into the sample space. I want us to look into the force in the triplet. So let's focus on the force in the triplet. Now, I want to look at the example. Okay? Now, I want to talk about sample space. In every experiment, there's going to be sample space. Sample space is just possibility of what could happen. Okay? Now, we're going to assume something now. When I'm tossing a coin, of course, you all know coin, right? That have head and tail, right? What are the possibilities? How many possibilities? 2, right? Is it that you see when you flip it once? Is it that you see head or you see tail, right? Well, what if you're working with a die? You know how many? What are the possibilities? This is my sample space now. Can you see that? This is what I'm talking about, die. That's going to be 1, 2, 3, 4, 5, 6. Okay? When I'm talking about, a coin, okay, depending on the numbers of times, depending on the numbers of times I actually flip the coin, please pay attention. Okay, if I'm working with a coin, okay, if I flip a coin one time, okay, my sample space is just going to be this. That's for one time. If I flip it twice, my sample space is going to change. Head, 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 tail, tail, head, tail, tail. If you want to know about this, you can use a tree diagram. One time, head, tail. Another time, head, tail, head, tail. And what are you going to see? Head, 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 tail, tail, head, tail, tail. That's what you see here. But do you know the one I'm showing you right now? The one I'm showing you right now, when I flip it 3 times, you know what I'm going to do? It's going to be easy. I'm just going to come here, put head and tail. I'm going to put another head and tail. I'm going to put another head and tail. I'm going to put another head and tail. And let's take a look at what we have right now. Please pay attention. Okay? Pay attention. Head, head, head. What do you see? Head, head, head. Can you see that? Head, head, tail. Can you see that? Head, head, tail. Until you get to the last one, until you get to tail, tail, tail. If I flip this 4 times, that is going to change. If you want to use tree diagram, then you continue to go. And you know what? It's just going to be expanding. Does that make sense? Now, what I'm showing you now, this is a sample space when a coin is tossed 3 times. I need questions. Is there any questions here moving forward? Is there any question moving forward? Everybody good? Oh, those of you at the back, you can hear me clearly, right? Anyone here having a trouble time hearing the way I talk, understanding the way I talk? Anybody here? You are good, right? Okay. If you don't understand the way I talk, if you are not getting this information, please let me know. Okay. Now I'm actually moving. Do you know example that we just talk about now? We just talk about one of the components in the probability model. I told you the probability model has a triplet. We just talk about sample space now, example of a sample space. Now we want to move to Collinet. Okay, to talk about Collinet, we want to talk about events. Let me tell you this. Events is a subset of a sample space. In a sample space, if I toss a coin 3 times and I'm looking for 3 heads, then this is the event that I'm talking about. So which is a subset of a sample space. But there's something I need you to pay attention to. Event is actually, it's a set of outcome of an experiment. It's a subset. But let me tell you this. Collection of events okay, is what actually translates into calling F. That's what translates to sigma algebra. But can I shock you? Do you know that the number of elements in a calling F is more than the number of elements in a sample space? Because my event may be different from your own event. Now we're going to see now how that is going to happen. And I wanted to see. You know, when you take a look at this, okay, when I choose a coin, when I choose a die, the possibility is 1, 2, 3, 4, 5, 6. This is the event of even numbers, right? This is another event. That's another event. You know what this event means? Less than 4. Number less than 4 is 1, 2, 3. You know that? Now, another event could be number greater than 5. Another event could be square root of maybe the number, the number that are perfect squared, which means there are so many events that we can think about. The collection of so many events that we can think about is what we call the calling F. And that is the reason why element in the calling F will be more than the sample space. Now you're going to see. We're going to see now. Just take a look at this. I'll come here first. Now, let's take a look at this. Please pay attention. Are you ready to pay attention? Look at this. If I toss a coin once, that's a sample space, right? If I toss a coin once, that's a sample space. Now, let's think about events that can take that we can have in that. We can have events of head, right? We can have events of tail. We can also have the events of both, right? And we can also have empty. Because of that, you know what is going to happen? Calling F, sigma algebra, is the same as a power of a set. Do you remember we did the power of a set the other time? What is the power of a set? The power of a set is the possible number of subset we can have, right? The possible number of subset we can have is the same thing as the possible numbers of events that we can have. So if I ask you to determine sigma algebra, which is the calling F, then I actually want you to find the proper set. Take a look at this. If you take a look at what I have here now, if I have this as a set, and I want you to find, to figure out the power of a set, what do we normally do? How many elements do we have here? We got 2, right? What is the formula for the power of a set? That will be 2 raised to power the number of elements in that set. So right now, we're having names. We're having head and tail, right? What is the cardinality? 2, right? The power of a set, if I want to know, the power of a set is 2 raised to power cardinality. So here it is 2 raised to power 2, which is going to be 4. And when you take a look at that, that's why you have 1, 2, 3, 4. Any question? So the calling F, now if you compare this and this, which one has more elements? It is the power of a set. The power of a set has more elements compared to the sample space, because the power of a set is talking about collection of any kind of event that we can think about. And because of that, that would be greater than the number of elements that we have in the sample space. Okay, so that's what I mean. Take a look at that. That's what I'm trying to say here. You're going to talk about the power of a set, so which is that. That's what I'm trying to say here. Okay, so if that is what I'm trying to say, now that you understand this, I'm actually going to, let me go a little bit. I'm going to come back here. Please pay attention. You know what we're dealing with right now, right? We're dealing with this guy. We're dealing with set of all events. Set of all events. Set of all events is a calling F. Also the same as the power of a set. Now, let's take a look at some property. We define that as this guy, right? That's a calling F, right? Say calling F, which is one of the triplets in probability model. Don't forget that is the second one. The first one is the sample space. The second one is the calling F. The third one is probability measure. Now let's focus on this guy now. I want to talk about some basic property of this guy now. Okay, so let's take a look at this. Let's see this. Please focus on the board. Focus on the board. Are you focusing? Look at that. Reason with that. You know what is that saying? Can somebody tell me? What is it saying? What is that saying? Can somebody tell me? What is it saying? I circle something now. Yeah, what is it saying? So say the sample space is inside the calling F. You know why? Let's see. Let's see whether it is inside. We want to see. We want to see whether it is inside. Let's see. Let's see whether it is inside. Do you see this guy? That's a sample space. It's inside. Can you see that? It's inside the calling F. It's always going to be inside the calling F. The sample space is always going to be inside the calling F. Does that make sense? Okay. Now, thank you for that. Send me a message for extra credit. Now, I'm actually moving. Now, we just talk about that. Okay. But let's take a look at this. Let's pay attention. If another set has is inside a calling F, okay? If another set is inside a calling F, the complement of this guy is also going to be inside the calling F. If you don't understand, ask me a question. If you don't understand what I said here, ask me a question. If a set S is inside a calling F, don't forget the calling F is very, very big. It has so many events that you can think about, possibility that you can think about, of event you can think about. Okay? So if a set S is inside a calling F, then the complement of that particular set also going to be in the calling F. Okay? Now, we now want to generalize now. Let's go into generalization now. Take a look at this. You know what a guy is saying? Please pay attention. Are you ready to pay attention? Because it's getting tough. And if you pay attention now, you're going to be fine. If you get stuck, ask me a question, okay? Now, if I now want to generalize, okay? I'm not talking about sets. I'm not talking about just one set now, okay? I want to talk about several sets. You know what this guy is saying? S high lies in calling F, where high starts from 1 all the way to N. You know what that guy means? Please pay attention. He's trying to say X1, set X1 lies in calling F. Set S2 lies in calling F until we get to set Xn. We got so many sets that lies in a calling F. Now, if so many of them lies in a calling F, okay, then what can we talk about? Then we can now say the combination. Okay, what I mean is this. If X1 lies in calling F, if X2 lies in calling F, until we get to Xn lies in calling F, then their union, bringing them together, we also lies in the calling F. So X1 union S2 union S3 union until we get to Sn also lies in calling F. That is what this guy is talking about here. Go ahead.
So 1, 2, and 3 are all like the conditions for the F to be a sigma algebra.
Exactly.
And then is this in the sample space as an element of the sigma algebra F? Is that only incountable, like infinity or like countable space, like if the sample space is countable?
Yeah, that's it. That's a very good one. Yeah.
Like,
So assumption here. Yeah. You're right. I'm assuming here that this particular one is countable. You know, just like what I said the other time, before you go into an experiment, you know possibility. Okay? Possibility. So we believe that elements in your possibility are countable. That's an assumption. The moment that changes, then the orientation is going to change. That's a good question. Okay. Now you understand this guy now, right? Let me tell you this. Math is easy. Statistical theory is easy. Only when you understand what each notation represents. So now you know what I just do now? Oh, 1 second. This guy now is this guy. Go ahead.
Why is it equal column instead of element column?
Which one? Do you mean this one? Oh, this one?
All the unions of sets like I, 1, 2, 3 through n create column f. Would be equal?
No. Not equal. So what he's trying to say is that, you know, this one now is this guy. If I bring if each, this is a condition. Let me see. Oh, I'm going to use this example. Minnesota is in United States. Wisconsin in United States. California in United States. If I bring all these states together, is it going to be in the United States?
Yeah, but wouldn't it also be like the same as the United States? Like, why is it?
What is going to be the same as the United States is where you put all of them, if all of them constitute United States.
Oh, okay, I get it.
Because this is what happened. If I consider S1 to Sn, if there is some other set that's also in the United States, you understand what I mean?
Yeah, like the n is 10, but there are 11 sets.
Exactly.
Then it wouldn't be. Okay.
But this is what happened. We are also captured. You know why? These are the other ones. This one means the set that I'm not talking about right now. If the set that I'm talking about right now is in column F, the one that I'm talking about is also in column F. And that is the reason why we cannot just say the one we're talking about now is exactly the one in the column F, because there's still other one in the column F. You know, I used to be happy when students ask questions, because statistical theory need to be discussed. Not that I'm just going to go to the board and just say, okay, S equal to Y equal to Z. That doesn't make sense. Let's discuss so that you understand it. Okay, now I'm going to move away from that now. Now we want to talk about probability measure. Now look at the story. We're talking about probability model. The probability model has a triplet. We just talk about omega, which is the sample space, collection of possible outcome. We talk about the column F, the sigma algebra, which is a collection of events. Now we want to talk about probability measure, okay, which is the third in the triplet. Do you know what probability measure is going to do? The probability measure will now assign probability to every outcome that you have, to every event that you have. And what is he assigning? He's going to assign a number. Please pay attention. Please pay attention. Take a look at what I'm trying to say here. You know what I mean? The probability measure, P, assign figures. What figures? The figure that go between 0 and 1 is going to assign that to the column F. Don't forget, the column F contains several events. So it's going to say, okay, for this event, your probability is this. For this event, your probability is this. What do I mean by probability in the actual sense? You know, when students hear probability, they're going to be scared. Probability in the actual sense means the numbers of times that event occur. Probability talk about frequency. Because some events occur more than some other events. Does that make sense? So that's what it means. So you can see here, assigning numbers in this 0, 1 to the column F. Now, For every event, now I need you to pay attention. Please pay attention for every event right now. Take a look at this. If I have event A, for every event A that you have in your calling F, then there exists a probability for it. That is what we call the P of A. Does that make sense? That means probability occur. Okay, probability is assigned to every event. But you know what? We now need properties. Before a function can be a probability function, then we need some property. Now we want to talk about property of non-negativity. We're also going to talk about property of normalization. Let's talk about non-negativity. So if you want to talk about the property, we're actually going to be talking about axioms. What do I mean by axioms? Axioms actually rules that guide probability. What is the rule number one? Please pay attention. The rule number one is this guy. Okay, that probability of any event cannot be negative. It can be 0 or greater than 0. Does that make sense? That's number one. That is what we call non-negativity property. Non-negativity. Non-negativity. Okay, property of probability. Don't forget, right now, we're talking about probability measure. Okay, we're talking about probability measure. So number one is non-negativity. Okay, and that is what that guy is talking about. Property number two is normalization. 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 You know what normalization property say? It say the probability of all possible events must be equal to 1, which is what I'm trying to talk about here. Please pay attention. Look at this guy. What is omega? What is omega? Omega is sample space. Sample space is possibility. The probability of possibility, it should be 1. Okay, and that's why you see here, we're going from the minimum 0, the highest is 1. So that is that. Now, another property that is very, very crucial is disjoint event. Please pay attention. Disjoint event. And I need you to pay attention. And you know what? This is where what you observed the other time. I need you to pay attention now to this number 3 axioms. Now, in number 3 axioms, in number 3 axiom, if I have A1, it's an event. A2, also an event. A3, also an event. And you know what? I have events that go forever. This is not countable. Does that make sense? But if they are disjoint, you know what disjoint means? Disjoint means they don't occur together. They occur on their own. There's no any interception. There's no any common thing between them. They are on their own. You understand what I mean? The disjoint event is just going to be stuff like this. It's going to be stuff like this. A1, A2, can you see that? Is there any overlap? Is there any overlap between them? Okay, that's what we mean by disjoint. Does that make sense? Now, if I now want to find, please pay attention, the probability of the union, A1 union, A2 union, A3 union, blah, 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 you know, it goes all the way. Okay, now let me tell you this. When events are disjoint, the probability of the union, okay, is actually going to be the sum of the individual probability. So this is going to be equal to the probability of A1 plus probability of A2 plus probability of A3 and so on like that. So the probability of the unions of a disjointed event will be equal to the sum of individual probability. Go ahead.
what would be an example of a power set that isn't disjoint?
What is the example of a power of a set that is not what?
Is not disjoint, because isn't by definition all power sets already disjoint because it has every unique possible variation?
Okay. I'm actually going to say this. It is not all events that are disjoint. But the one we're focusing now, everything that we do in math and statistics is based on assumption, right? Now, we're assuming now, when we're talking about disjointed event that don't overlap, we're still going to talk about event that overlap. We're coming there. But what we're discussing right now, okay, if events are not overlapping, okay, the probability of their unions will be equal to the sum of the probability. For instance, if I want to focus on two events, okay, A and B, okay, if I do this, if I find the probability of A union B, and if A and B are disjoint, okay, it is just going to be this. Okay, now we call this situation mutually exclusive. But just 1 second. We have another situation, okay? If there is an element of overlapping, this is going to change. This is going to change to this. This is now become non-mutually. We're coming to this. Does that make sense? So when you talk about mutually, where they disjoint, it's only going to be some. But when you talk about situation, like this guy down here, this guy is just this. But this guy is just this. Can you see? Can you see that? We're coming there. Does that make sense? Ask your question.
Say, if you have a probability space where all events are disjoint, does that mean that like each event is like independent from each other?
Oh no. This is what we are careful with the way we use words in statistics, because independent event has a different definition. I have mutually exclusive event, I have non-mutually exclusive event, I have independent event, I have dependent event. So we're coming into that. That makes sense? When you ask question, when you say out your mind, that corrects some things that you have within you. Does that make sense? I like the way you're talking now. Now, do you know that this is for two events, for disjointed, but this is for the general one. Okay? So if I want to write this one in short form, this is it in short form. And the sum in short form, that is that. So this one now is the shortest way of writing this and that. Does that make sense? Okay, now I want us to move right now. We are now going into the theory. And because of that, I'm going to take my time. Now, let's take a look at theorem number 1. Because you know why? What are we dealing with? The whole course is probability. It's about statistical theory, it's about probability theory. And don't forget the probability model that we're using. It is called probability model because there is a measure called probability measure. Don't forget in the specification, you have a triplet, you have the sample space omega, you have the Colin F or sigma algebra, then you have a probability measure, but we're going to spend a lot of time on probability measure. Okay, so number 1, let's talk about this first proposition. And I need you to pay attention. Do you know that event A, I'm actually going to use Venn diagram for you to understand. If I have a sample space, the whole thing is a sample space. And this is event A. Outside is A complement. If you take a look at that, they are disjoint, right? This guy and this guy are disjoint. If they are disjoint, if you want to follow that law, of disjoint, what is going to happen? It's going to be probability of A complement union A, right, equal to what? Equal probability of A complement plus probability of A, right? If I had, please pay attention. We're doing math right now. Pay attention, okay? If I had A to A complement, what do I have? I have the omega. So I'm actually going to say A complement union A is omega. Now, what is the probability? Then that is the probability of that. What is the probability of omega? 1. So this is going to be 1. Then I'm going to say this equal to 1. Okay? If this equal to 1, if you take a look at this, if I want to get probability of A, it can be 1 minus that. If I want to get the probability of A complement, it's 1 minus that. That is proposition number 1. Any question? That's proposition number 1. That is what we call the law of complements. Okay. We want to go into composition number 2. In the composition number 2, pay attention. Pay attention. If I have 2 sets, and A is a subset of B, if A is smaller than B, then we expect probability of A to be less than probability of B. Or at most, they're going to be equal. And that's what this guy is trying to talk about. If A is a subset of B, the probability of A is less or equal to B. How can we prove that? Please pay attention. If you want to prove this, I think at this point, I'm not going to rush because we're getting into the theory. So I'm going to continue from this on Monday. But let me tell you where we are now. We are now in probability theory. But if you pay attention in class, it will be so easy. That's what I got for you today. Make sure you all stay safe and have a lovely day. Bye.